everyone, I am Arunima and I am a PhD student here at the Max Planck Institute for Radio Astronomy. Today I will be providing some updates from the radio timing analysis of a binary pulsar in a globular cluster, and I am presenting this work on behalf of the TROPIM and MEAT-10 globular cluster collaboration. So what I thought while making the talk was that why would I bother making you stuck with this long title with this big words? So I came up with a short one. So what we are going to look at today is a case study of NGC 1851A, which is a binary system that consists of a millisecond pulsar with another neutron star in a binary orbit. And then I thought maybe I can give you a bit of a spoiler too. So, contrary to what we earlier thought NGC 1851A to be, it seems to consist of a millisecond pulsar with a white dwarf companion in some sort of a triple configuration instead of a binary. Now, Lars mentioned about many of these triple systems this morning in his talk. So what makes this one different is that it is in a globular cluster. And that is also the reason why this question mark at the end of the spoiler comes from. So you have to stay tuned. Now the good thing about giving a talk towards the end of the conference is that everyone has introduced everything for you. So you can straight away start talking about the target, which is what I am going to do. So PSR J0514-4002A consists of a 4.99 millisecond pulsar in a very eccentric binary orbit with a massive companion, and its orbital period is about 18.8 days. This was the first pulsar that was discovered in the globular cluster NGC 1851, and that is why it is also designated as NGC 1851A. After its discovery back in 2004 with observations from the Giant Meter Wave Radio Telescope or the GMRT in India, further timing updates were done with observations from the Green Bank Telescope and then later again with the GMRT in India. So the motivation for the updated timing analysis of this system is to address the unresolved questions from the last work on this system that was done by Ridolfi et al. 2019. Now firstly, they observed a very unusually high and positive orbital period derivative for the system, which is this large value given here. And this value could not be explained by any mass loss from the system, by the acceleration effect of the globular cluster, or even by the emission of gravitational waves from the system. Now second one was that they measured a proper motion for the system, which translated to a transverse velocity which was orders of magnitude higher than the cluster central escape velocity. So what this suggested was that the pulsar was not bound to the cluster at all. And finally, there was an ambiguity regarding the exact nature of the companion to the pulsar because there was no detection of a Shapiro delay in the system. Just to give you a quick reminder, Shapiro delay is a relativistic light propagation delay, as you can kind of see in the diagram here, due to the gravitational field of the companion. Now this plot here on the left is what we call as a mass-mass diagram with companion mass versus pulsar mass ranges. So under the assumption of the general theory of relativity, if you measure a post-Keplerian parameter or a relativistic parameter for a binary system, you can plot it as a curve on this diagram, and the intersection point of these various curves give you the pulsar and the companion mass. So this was the plot that they had with the work done by Ridolfi et al. 2019. Now what we did is we took some observations from the GMRT in India and some with the MEAT-10 radio telescope in South Africa. With the GMRT we observed this system over about 12 epochs between 2018 to 2020 with the band 3 receiver. And with the MEAT-10 we observed this system for about 2.5 years with 20 observations using both the L-band and the UHF receivers. This led to an extension of the dataset by about 5 years, leading us to a total timing baseline of about 19 years for the system. So the plot here on the left shows the post-peak timing residuals between the timing model of the pulsar and the observed arrival time of the pulses from the pulsar. So as you can see, the residuals are very well distributed, which suggests that this timing model predicts the arrival time of the pulses very well. Now this timing model is exactly which was shown here on the right. I would rather say it's a glimpse because there are many more parameters. But this basically includes a collection of various astrometric, spin and binary parameters for the system. Now one parameter specifically I would like to draw your attention to is this here, which is called as the reference epoch. which is basically the epoch at which all of these parameters were determined and noted for this system. Moving on to what the results that we obtained with this extended timing analysis is that we measured a new observed orbital period derivative value for the system, which is this value as given here, and this is exactly according to what is expected due to the acceleration of the mean field of the globular cluster. So the anomaly that was there regarding the very high and unusual value of the observed orbital period derivative is now resolved. Next, we measured a very precise proper motion for the system, which is about 3 milliarc seconds per year, and this corresponded to a transverse velocity of about 30 kilometers per second with respect to the cluster's core. Now the cluster has a central escape velocity of about 43 kilometers per second. So this basically helped us conclude that the pulsar is actually associated to the cluster. This plot here on the right shows the exact position of the pulsar with respect to the core of the globular cluster. Out of many of the binary parameters that we measured for the system, I've noted a couple. First one is a mass function for the system, which is about 0.14 solar masses, which indicates that the pulsar has a massive companion. And we also measured the inclination of the system to be around 61 degrees. Now, we also precisely measured two relativistic parameters for the system, which are the rate of advance of periastron and Einstein delay, which are given by these values here. And as I mentioned earlier, that once you measure these parameters, you can use GR and then make this diagram where each of these parameters go as a curve. And you can see that there is this point of intersection of the two curves, and of course then we obtain the exact masses of the pulsar and the companion. So the mass of the pulsar in this system has a mass of about 1.39 solar masses, and the mass of the companion is about 1.08 solar masses. Now the lightest neutron star that is expected theoretically is about 1.17 solar masses, and also from observations. So this basically helps us conclude that the companion to the pulsar is most likely a heavy white dwarf companion. We also measured very precisely the observed spin period derivative for the system as given here. Now in a globular cluster, the different accelerations, like from the cluster, from the proper motion effect, they affect the spin and the orbital period derivative alike. So you can use an equation like this to calculate the intrinsic change in the spin period and the characteristic age as given here. Now, other than the first frequency derivative, we also precisely measured the second and third frequency derivative and some other parameters that I already mentioned to you. And this is exactly the reference epoch that I was talking to. So this is sometime back in 2022, which is close to the end of our timing baseline and the epoch at which this work is based. Now, if you look at the exact same parameters from the work done by Rudolph et al. 2019, where the epoch was set to way earlier, like about 10 years back in time, the values are quite different, but I would like to draw your attention particularly to these two values. About the first frequency derivative, I'll come to that in the next slide. Let's look at the characteristic age. So if you look at this characteristic age, it's about 3 gigayears, which is from this work at this epoch, and this one is significantly different. Now, characteristic age is an intrinsic property, and you do not expect it to change depending on which epoch you are measuring it at. And also, why is it so different is because this age kind of indicates that the pulsar is one of the youngest pulsar in this cluster. This one makes it one of the oldest, so something is going wrong. This is just a more visual idea of how the frequency derivatives change. So the observed spin frequency derivative changes by a factor of 27 between the two reference epochs, and this is well within the timing baseline. So this is basically a manifestation of the change in the line of sight acceleration, which is a very high line of sight jerk as given here. Now literature suggests that the jerk for a pulsar in a globular cluster can have two main contributions. And the first and the generally dominant one is the globular cluster's mean field itself. But for NGC 1851A, taking its parameters and the location at which it is in the core, this is the maximum possible line of sight jerk that can be induced by the mean field of the cluster, and this is 20 times less than this observed value. So this difference and this extra contribution is basically coming from this second factor that I was mentioning about, which is the presence of a nearby star around this binary. Now this can have two types of scenarios. The first one is that this could be the part of a hierarchical triple configuration, where there is the inner binary here and there is a third mass externally in a stable outer orbit. Or it could be possible that this is a flyby encounter of a nearby star in the globular cluster, and there is the binary and it is moving in a hyperbolic orbit around that. So what we have done here is that we have looked at these two situations differently. The plot here on the left shows a hierarchical triple configuration, the solutions for various elliptical orbits with different eccentricities. And as you can clearly see that for an external mass in a hierarchical triple, it can have a wide range of masses as shown here, and also has to have orbital period more than hundreds of years. Coming to this hyperbolic encounter with a close mass, which is modeled through like a flyby encounter with a nearby mass in the globular cluster's core, we see here the masses versus the velocities of each of these solutions at infinity. For a hyperbolic scenario, the eccentricities can go anywhere, there is no limit. But for here, in our work, we have only taken eccentricities from 1 to 5. Now the next question that we addressed is what happens to the validity of our mass measurements under the influence of this third body. So we took this exact same solutions that I showed in the previous slide, and we calculated the tidal contribution of this external body to the rate of advance of periastron that we measured, as I mentioned a few slides back. So for any kind of configuration, for whatever eccentricity you can come up with, and for all of these solutions, the maximum tidal contribution to the rate of advance of periastron is at least 3 orders of magnitude smaller than the observed value. So what this basically says is that the masses are not affected and that our mass measurements are robust. Coming back to the question that made us go through all of this new solution is that what happens to this characteristic age? So, like I mentioned, the characteristic age is directly dependent on your observed spin and orbital period derivative. We saw that there is a very high line of sight jerk that we are seeing for this system. Now this line of sight jerk, the influence of this value on the frequency derivative, that is accounted for by the higher order frequency derivatives that we measure. But this jerk also has a similar significant contribution to the orbital period derivative, and the contribution is larger than the measurement uncertainty of the parameter. So what we then need to do is that we need to account for higher order orbital frequency derivatives also, which we estimate from the corresponding spin frequency derivatives as given here, and these are the values for the second and third orbital frequency derivative. This eventually gives us a refined measurement of the observed orbital period derivative, this value here, and again using this equation one can estimate the intrinsic change in the spin period. We measure the intrinsic spin period change and we also estimate the characteristic age, and as you can see that irrespective of the reference epoch at which you are measuring it, the characteristic age values are completely consistent. So this is just a summary of this radio timing analysis update that we have done on this system. I've run out of time, so I'll leave you with the summary, but I'll just mention that in addition to resolving the earlier questions that we had, we also have this amazing new results with this pulsar in some kind of a triple configuration. So yeah, I'll take any questions if you have any, and I'll leave the summary for you. Questions? No, it's based on the mass, that's why we say that it's most likely a heavy white dwarf companion. So this globular cluster is very far away, it's 12 kiloparsec away. So we currently don't have any multi-wavelength studies for this at the moment. Like I mentioned, so the lowest neutron star mass that we know is 1.17 solar masses. And this is about 1.08 solar masses. So that's like right away an indicator that it's below the lower limit and it is most likely a white dwarf.
What's the error bar in the measurement of the mass?
Wait, you have to wait. Sorry. Oops.
Okay. Okay. Yeah. Any other question? One last question? If not,
globular cluster? Yeah, so it's basically you use a model of the cluster, like you use like a spherically symmetric model. The main parameters you use are like the velocity dispersion, then you use the radial separation at which a particular pulsar is located, like this is like 0.08 arc minutes away from the core of the cluster. So if you take this model and basically use these parameters, you can come up with the maximum possible value.
Just add something on that. So there's another constraint, which is that your orbital period derivative divided by the orbital period cannot be larger than the spin period derivative divided by the spin period.
Because the pulsar is spinning down, so the intrinsic
Because the
derivative would
pulsar has to
always be
spin
positive.
down. So, and if they're both affected by the same acceleration, you have a hard limit there. And that's why that earlier spin orbital period derivative would not be caused by acceleration. Because otherwise you have a very large negative spin down.
Okay, so let's thank Arunima again.